This code is written in Python and uses the TensorFlow library, which is commonly used for machine learning and artificial intelligence tasks. The code performs two primary tasks. Firstly, it imports the TensorFlow library and then prints the version of TensorFlow that is currently installed. This is useful for debugging purposes or to ensure that the correct version of TensorFlow is being utilized for a specific project or set of code requirements. Secondly, the code imports the datetime module, which is part of the Python standard library and provides functions for dealing with dates and times. It then prints the current date and time, formatted in a way that indicates when the notebook, presumably a Jupyter notebook or similar interactive development environment, was last run from start to finish. This can be helpful for record keeping or tracking when experiments were executed. The purpose of this code snippet is to generate a synthetic dataset consisting of points grouped into a circular pattern. This is achieved by using the make_circles function from the sklearn.datasets module, which is a part of the scikit-learn library. The code specifies that 1,000 examples, n_samples equals 1,000, should be generated. The make_circles function is then called with three parameters: the number of samples, n_samples, the amount of Gaussian noise equals 0.03. Added to the data to make the task more challenging by introducing some variation to the points, and a seed for the random number generator, random_state equals 42, to ensure reproducibility of the dataset. The function returns a tuple containing the feature set x and the corresponding labels y. X contains the generated points coordinates, structured as a two-dimensional NumPy array, whereas y is a one-dimensional NumPy array containing the class labels 0 or 1, indicating to which of the two circles each point belongs. This code is intended to create a scatterplot using the matplotlib library in Python. It takes a matrix or two-dimensional array x, presumably containing numerical data, and plots points using the values from the first, x:0, and second, x:1, columns of the array as the x and y coordinates for each point respectively. Additionally, the color of each point is determined by the values in the array y, which contains labels or categories for the corresponding points in x. The CMAP parameter specifies the color map to use for coloring the points, with this particular code using the RDYLBLUE color map, red-yellow-blue spectrum. This type of plot is commonly used to visualize the distribution and relationships of data points within a two-dimensional space, often in the context of machine learning for tasks like clustering or classification. This snippet of code is setting up, compiling, and training a simple neural network using TensorFlow's Keras API. Initially, it sets a random seed for reproducibility, ensuring that the same random numbers are generated each time the code is run, which is useful for debugging and comparing model results. First, it creates a neural network model called model_1 that is composed of a single layer with a single neuron, suitable for a binary classification task, hence the use of a single output unit. Second, it compiles the model using the binary cross-entropy loss function, which is appropriate for binary classification problems. The model uses the stochastic gradient descent (SGD) optimizer to iteratively adjust the weights of the network during training. The model will also track the accuracy metric during training to evaluate performance. Lastly, the model_1.fit call trains the model for 5 epochs on the provided training data x and labels y. During each epoch, the model makes predictions, calculates the error, loss, uses the optimizer to update the model, and repeats this process, attempting to minimize the loss and improve the accuracy over time. This code snippet is related to training a machine learning model using a function named model_1.fit. It trains the model on the dataset represented by x features/input and y targets/output for a total of 200 epochs. An epoch is one complete pass through the entire dataset. Training for more epochs allows the model additional opportunities to learn patterns in the data. The argument verbose equals 0 is used to suppress the output of the training progress for each epoch, which can otherwise be quite verbose and produce a lot of output, especially when training for many epochs. After the training is completed, the model_1.evaluate function is called, which assesses the performance of the trained model on the same dataset it was trained on. This provides some measure of how well the model has learned to predict the outputs from the inputs. However, evaluating on the same dataset used for training does not provide information about the model's ability to generalize to unseen data, which is typically of greater interest. The purpose of this code is to create, compile, and train a neural network model using TensorFlow. The random seed is set to 42 with tf.random.set_seed 42 for reproducibility, ensuring that the same pseudo-random numbers are generated each run, which is useful for debugging and comparing models. The code first defines a sequential model named model_2 with two dense layers, each with one output unit. These layers are going to be connected sequentially in the model, with the output of the first layer serving as input to the second. The model is then compiled using the binary cross-entropy loss function, which is appropriate for binary classification tasks, and the stochastic gradient descent (SGD) optimizer is used to update the weights during training. The accuracy metric is specified to monitor the performance of the model during training. Finally, the model is trained on the data provided by X features and Y labels for 100 epochs. The verbose equals 0 argument is used to prevent the training progress output from being printed, resulting in a cleaner output. The outcome will be a trained model with weights adjusted to predict binary outcomes from the input data X. The code provided is written in Python and uses the TensorFlow library to create and train a neural network model for binary classification. The purpose of the code is to define the model architecture, compile it, and fit it to the training data. First, the code sets a random seed for TensorFlow operations. This is done to ensure the reproducibility of the results, meaning that each time the code is run, it will produce the same outcomes, given that the input data X and Y remain unchanged. The model, named model_3, is then created using TensorFlow's Keras API. It is defined as a sequential model, which indicates that it consists of a linear stack of layers. This particular model has 3 layers, each being a dense, fully connected layer. The first dense layer has 100 neurons, the second layer has 10 neurons, and the final layer has 1 neuron. The number of neurons and layers in a model can affect its capacity to learn from data. Next, the model is compiled with a specific set of configurations needed for the training process. For loss function, the model uses binary cross-entropy, which is common for binary classification problems. The optimizer chosen is Atom, which is an adaptive learning rate optimizer that is generally more efficient than SGD, stochastic gradient descent. The metrics parameter is set to monitor the accuracy during training, which is a typical metric for classification problems. Finally, the model is trained, or fitted, to the data by passing in the input features X and the target variable Y. The epochs parameter is set to 100, indicating that the model will be trained for 100 iterations over the complete dataset. The verbose parameter set to 1 will display detailed progress of the training process in the console. This code defines a function plot_decision_boundary that visualizes the decision boundary of a machine learning model. This visualization helps to understand how the model separates different classes within a dataset. The function accepts 3 parameters: model, which is the trained model used to predict the classes, X, which are the features of the dataset, and Y, which are the true labels for the dataset. The code starts by calculating the minimum and maximum values of the features in X and uses these limits to create a mesh grid with a little margin, 0.1, on each side. This grid covers the feature space and is used to make predictions for every point on the grid to determine where the decision boundary lies. Next, it creates an array X_n of every combination of grid points as input for predictions. The model's predict function is then applied to this grid to get the predicted labels for these points. The code also checks whether the model is performing multi-class classification, more than 2 classes, or binary classification 2 classes, by checking the shape of the model's output. For multi-class, the prediction with the highest probability using argmax is selected. For binary classification, the maximum of the predicted values rounded off to the nearest integer is chosen. Finally, the plt.contour function is used to draw the decision boundary using the predictions, and plt.scatter plots the original dataset with true labels in the feature space. It sets the limits of the plot using the minimum and maximum values of the mesh grid, and then displays the boundary along with the data points using different colors to visually distinguish between different classes. The function assumes that the matplotlib library is imported and available under the namespace plt, although the import statement is not shown in the provided code. The code snippet provided is invoking a function called plot_decision_boundary, passing in 3 arguments, model_3, X, and Y. This function is likely designed to visualize the decision boundary that the provided model, model_3, has learned based on the feature data x and the target variable y. The decision boundary is a concept in machine learning that separates the different classes that the model has been trained to distinguish. When plotted, it allows us to see how well the model can differentiate between classes based on the training data. In a two-dimensional feature space, this boundary can often be represented as a line, curve, or contour. This particular code does not perform any training or prediction. It solely focuses on displaying the decision boundary of an already trained model_3, for the given dataset, x and y. It helps in understanding and interpreting how the model is performing and what kind of decisions it makes when classifying new data points. The code model_3.summary is a method call in Python that is likely associated with a machine learning model or neural network created using a library like TensorFlow or Keras. The summary method is designed to provide a quick and concise description of the model's architecture. When this method is called on a model object named model_3, it will print a summary of the model to the console. This summary typically includes information about the layers of the model, their respective output shapes, and the number of parameters, weights, and biases in each layer. It also includes the total number of parameters in the model. This summary is useful for understanding the structure of the model, debugging, and verifying that the layers are connected as expected. The code provided is for setting up, compiling, and training a neural network model using TensorFlow, specifically the Keras API. The purpose of the code is to create a simple feed-forward neural network for regression tasks and train it on some dataset represented by x_reg_train and y_reg_train. The first line tf.random.set_seed, 42, sets the random seed to ensure that the results are reproducible. This means that the random operations inside TensorFlow will produce the same results on every run. The following lines define the model_3, as a sequential model, which is a linear stack of layers. The model consists of 3 densely connected layers. The first layer has 100 neurons, the second layer has 10 neurons, and the output layer has a single neuron, which is typical for a regression task where the goal is to predict a single continuous value. The compile method configures the model for training. In this case, the loss function is set to mean absolute error, may, which is appropriate for regression problems. The optimizer is set to atom, which is an algorithm used to change the attributes of the neural network, such as weights and learning rate, in order to reduce the losses. The metric used to judge the performance of the model during training is also mean absolute error, may. Finally, the model is trained using the fit method, which takes the training data x_reg_train and y_reg_train as inputs. The tf.expand_dims, x_reg_train, axis equals -1, function changes the shape of x_reg_train to ensure it has the right dimensions for inputting into the neural network. The training process is run for 100 epochs, which means the entire dataset is passed through the neural network 100 times in an iterative fashion to update the model's weights to minimize the loss function. This code is using a trained model named model_3 to make predictions on a dataset referred to as x_reg_test. After generating the predictions, denoted as y_reg_preds, it proceeds to visualize the results using matplotlib, a plotting library for Python. A new figure with a size of 10 by 7 inches is created for the plot. The training data, x_reg_train and y_reg_train, are plotted as blue points, while the test data, x_reg_test and y_reg_test, are plotted as green points, illustrating the actual data the model is being evaluated against. Additionally, the predictions made by the model on the test data are plotted as red points. Squeezing the y_reg_preds array indicates that if it contains a single dimension of length 1, this dimension is removed to match the shape of x_reg_test for plotting. A legend is included in the plot to differentiate between the training data, testing data, and the model's predictions. This visualization is helpful for assessing the performance of the model by comparing its predictions to the actual values. This code snippet is written in Python and uses the TensorFlow library to create and train a simple neural network model for a binary classification task. The code begins by setting the random seed for TensorFlow's random number generator to 42. This is done to ensure reproducibility, so that the neural network's initial weights are initialized the same way each time the code is run, and therefore the training process can be repeated with identical results. Next, a sequential model named model_4 is created using the Keras API, which is part of TensorFlow. The model consists of two layers. The first is a dense, fully connected layer with one unit and a linear activation function, and the second is another dense layer with one unit that serves as the output layer. Typically, the output layer of a binary classification model would use a sigmoid activation function. However, since no activation is specified for the output layer in this code, it defaults to a linear activation, which may not be appropriate for binary classification tasks unless it's followed by a thresholding step later on. The model is then compiled with a binary cross-entropy loss function, which is appropriate for binary classification problems. The Atom optimizer is used to adjust the weights during training, with a learning rate of 0.001. During the compilation, the model is also set to track the accuracy metric to evaluate performance. Finally, the model is trained by fitting it to the data represented by placeholders X and Y, which are assumed to be the features and labels of the binary classification dataset, respectively. The model is set to train for 100 epochs, which means it will iterate over the entire dataset 100 times, during which the optimizer will adjust the weights to minimize the loss function. Overall, this code constructs a basic neural network for a binary classification problem, compiles it, and runs the training process. However, since the output layer does not include an activation function suitable for binary classification, further adjustments might be necessary for the model to perform well on a binary classification task. The given code configures and trains a machine learning model using TensorFlow, a popular deep learning framework. Initially, the random seed for TensorFlow's random number generator is set to 42, ensuring reproducibility of results across different runs. Next, a sequential neural network model named model_5 is created with two layers. The first layer is a dense, fully connected layer with one neuron and a ReLU, rectified linear unit, activation function, which is a nonlinear activation function common in deep learning models. The second layer is a dense layer with one neuron, serving as the output layer. The activation function for the output layer is not specified, which implies a linear activation by default. The model is compiled with the binary cross-entropy loss function, which is suitable for binary classification problems. The Atom optimizer is used for adjusting the weights of the network during training, and the metric set to track is the classification accuracy. Finally, the last part of the code fits the model to the data provided in variables X and Y over 100 epochs. Fitting the model involves running a process that adjusts the weights through backpropagation using the data samples provided, effectively training the neural network to learn the underlying patterns to make predictions based on the input data X and the output labels Y. The history object will contain the history of training loss and accuracy metrics for each epoch, allowing for evaluation of the model's performance over time. The code defines and trains a simple neural network using TensorFlow, which is a popular machine learning library. It starts by setting a random seed to ensure the reproducibility of results. Then a neural network model is created using Keras, a high-level neural networks API running on top of TensorFlow. The neural network, named model_6, is composed of a sequence of layers, which includes two hidden layers with 4 neurons each using ReLU, rectified linear unit, as their activation function, followed by an output layer with a single neuron. The model is then compiled, which is a necessary step before training. During compilation, the loss function is specified as binary cross-entropy, which is commonly used for binary classification problems. The optimizer used is Atom with a learning rate of 0.001, which is a standard choice for training neural networks due to its efficiency in converging. The model's performance will be assessed based on accuracy, which is a common metric for classification problems. Finally, the model is trained on some dataset X, features, and Y target, for a total of 100 epochs. During each epoch, the model will attempt to learn the patterns by adjusting its weights to minimize the loss function. The training process result is stored in a variable called history, which can later be used for analyzing the model's training progression, such as plotting the accuracy or loss over the epochs. The given line of code is a Python statement which uses the evaluate method, most likely from a deep learning framework such as TensorFlow or Keras, to assess the performance of a neural network model named model_6. This method takes in two parameters, X and Y, which represent the input data and the corresponding target data, respectively. The purpose of the evaluate function is to compute the loss value, and often additional metrics such as accuracy, for the given input, x, against the known outputs, y. It essentially tests how well model_6's generated predictions match the expected results, typically after the model has been trained with a separate set of data. The output from this method will be a quantitative measure of the model's performance, which can be used to infer how well it will generalize to new, unseen data. This method is vital for understanding the model's accuracy and tuning it for better results. The purpose of the code snippet provided is to visualize the decision boundary created by a machine learning model designated as model_6. The function plot_decision_boundary is likely a custom or a library-provided function that takes a machine learning model, input features x, and target variables y as arguments. When the snippet is executed, it will generate a plot depicting the decision boundary which differentiates or separates the different classes in the feature space as learned by model_6. This model appears to have two hidden layers, hence the mention in the code comment. Visualizing the decision boundary is a common way to understand how well a model has learned to distinguish between different classes based on the given data features. The code snippet is used to create, compile, and train a simple neural network model using TensorFlow's Keras API. Initially, it sets a random seed for TensorFlow's random number generator to ensure reproducibility of results. This is followed by the creation of a sequential model named model_7, which consists of 3 dense, fully connected layers. The first 2 layers have 4 neurons each and use the ReLU, rectified linear unit, activation function, which is common for hidden layers. The last layer has 1 neuron with a sigmoid activation function, indicating that the model is likely addressing a binary classification problem. The model is then compiled with the binary cross-entropy loss function, which is appropriate for binary classification tasks. It uses the Atom Optimizer, a popular choice for training neural networks due to its efficiency and adaptive learning rate properties. The model also tracks accuracy as a performance metric. Finally, the model is trained on data X, features, and Y binary labels for 100 epochs, meaning the entire dataset is passed through the network 100 times during training to adjust the model's weights. The verbose parameter is set to 0, which means no training progress output will be displayed during the training process. The training process history, such as loss and accuracy for each epoch, is captured in the history object, which can be used for further analysis or plotting performance over time. The code snippet is performing an evaluation of a machine learning model designated as model_7 on a set of data. The .evaluate method is likely from a machine learning library, such as TensorFlow or Keras, where it is typically used to assess the model's performance. It takes 2 arguments, x and y, which represent the features and labels of the dataset, respectively. The method computes the loss and any additional metrics that were specified when the model was compiled, returning the results. This evaluation will help determine how well model_7 has learned to predict the labels from the features and how it might perform on unseen data. The purpose of this code is to display a visual representation of the decision boundaries generated by a machine learning model, referred to here as model_7. When it is applied to a dataset with input features x and target variables y, specifically, the model appears to have used ReLU, rectified linear unit, and sigmoid activation functions as part of its architecture. The function plot_decision_boundary is responsible for producing a graphical plot that illustrates how the model separates the data into different classes based on its learned decision boundaries. This visualization aids in understanding how well the model is able to discriminate between different classes and can provide insights into the model's performance and potential areas for improvement. This code snippet creates a tensor named using TensorFlow, a machine learning library. The tensor A is formed by creating a range of integers from -10 to 10, including -10 and excluding 10, resulting in a 1D tensor or vector containing 20 elements, -10, -9, 8, 9. The tf.range function creates the sequence of integers, and then tf.cast converts the elements of this sequence into floating point numbers, creating a tensor of type tf.float32. This conversion is common practice when preparing data for input into models that expect floating point inputs. The resulting tensor can be used for various purposes like testing model operations, as it simulates the kind of numerical data that might be fed into a neural network. The purpose of this code is to visualize the data contained within a tensor, referred to as A, by plotting it on a graph. This is achieved by using the plot function from the matplotlib library, which is a popular visualization library in Python, commonly imported under the alias PLT. When plt.plot_a is executed, it generates a line plot representing the values in A along the y-axis, with their corresponding indices on the x-axis. The plot helps in understanding the distribution, trend, or pattern within the tensor's data. However, without prior code context, like import statements or definitions for A, the library being used, and the type of the tensor A remain unspecified. This Python code defines and uses a sigmoid function, which is a common activation function in machine learning and particularly in neural networks. The sigmoid function, mathematically expressed as 1/1 plus exp x, maps any input value x to an output value between 0 and 1. This can be particularly useful for binary classification, as it converts numbers into probabilities. The code begins by defining a sigmoid function that takes an argument x. Within the function, the TensorFlow library's exponential function tf.exp computes the exponential of x. The result is then used in the sigmoid formula. After defining the sigmoid function, the code applies this function to a tensor A, which is supposed to be provided elsewhere in the context. The sigmoid function is often used in the output layer of a binary classifier to obtain probabilities that indicate the likelihood of an input belonging to a particular class. The reference to TensorFlow's documentation suggests that this is an implementation or example usage inspired by TensorFlow's own sigmoid functionality. The code snippet appears to be a part of Python code, likely using the matplotlib library to create a plot of the sigmoid function applied to a tensor A. The sigmoid function typically takes a tensor or array as input and applies the sigmoid operation to each element, which is an activation function commonly used in neural networks. The sigmoid function has an S-shaped curve and is defined as 1/1 plus exp x, where exp is the exponential function and x is the input value. Assuming sigmoid A returns an array-like object with the sigmoid function applied to all elements of tensor A, the plt.plot function is then used to plot these values on a 2D graph. The plot would show the values of the tensor on the y-axis, with the x-axis implicitly representing each element's index or a range of input values provided by the tensor A. The semicolon at the end of the code line suggests this might be in an interactive environment such as Jupyter Notebook, where the semicolon is used to suppress the output of the last line to make the output neater. However, as this line of code is taken out of context, assumptions about the library imports, definition, and initialization of A and earlier definitions in the code are being made based on typical usage patterns. This code defines a Python function relu x, which implements the rectified linear unit ReLU activation function commonly used in neural networks. The ReLU function outputs 0 for any negative input and outputs the input itself if it is positive or 0. This is achieved using the tf.maximum function from the TensorFlow library, which takes two inputs and returns the maximum of the two. Therefore, tf.maximum 0, x, will return 0 if x is negative and x if it is positive or 0. After defining the ReLU function, the code applies this function to a tensor A. The returned result will be a tensor where all the elements of A that were negative are replaced with 0, and all non-negative elements remain unchanged. This operation is commonly used as an activation function in neural networks to introduce nonlinearity and to help the network learn complex patterns. This code snippet refers to a function tf.keras.activations.linear from the TensorFlow library, which is a popular machine learning framework. The linear activation function is one of the simplest types of activation functions used in neural networks. The purpose of this particular code involving tf.keras.activations.linear, A, is to apply the linear activation function to some input data A. The linear activation function does not alter the input data, it simply returns the input as the output. In other words, if you apply this function to any input, the output will be the same as that input. This function might be used in a neural network layer where no nonlinear transformation is desired, which can be the case in simple regression tasks or as the output of the last layer in a multi-class classification problem when raw logits, pre-softmax scores, are required. This piece of code is checking whether applying a linear activation function to a tensor A changes the tensor in any way. In TensorFlow, tf.chars.activations.linear is essentially a no-op activation function, which means it should return the input without any modification. The code compares the tensor A before and after applying the linear activation function. If the linear activation function works as expected, which it does, it will not alter the input, and thus A equals tf.chars.activations.linear, A, should evaluate to true. This is checking the property of linearity where the activation function f, x, equals x, so the output is the same as the input. This code segment is responsible for creating, compiling, and fitting a simple neural network model using the TensorFlow and Keras deep learning libraries in Python. Firstly, it sets a random seed to ensure reproducibility of the results. It then constructs a sequential model, model_8, with 2 hidden layers, each consisting of 4 neurons and using the rectified linear unit, ReLU, activation function, followed by an output layer with a single neuron using a sigmoid activation function appropriate for binary classification tasks. After defining the model architecture, the code compiles the model specifying a binary cross-entropy loss function, the atom optimizer, with a learning rate of 0.01, indicating that the model's parameters will be updated in larger steps than the default rate, and an accuracy metric to monitor the training process. Finally, the model is fitted on the provided training data, x_train and y_train, for 25 epochs, which means the gradient descent optimization algorithm will cycle through the entire dataset 25 times to adjust model weights and minimize the loss, effectively learning from the dataset. The given code evaluates the performance of a trained machine learning model, referred to as model_8, on a test dataset consisting of features x_test and corresponding labels y_test. The model's evaluate function is used to compute 2 key metrics, the loss and the accuracy of the model when making predictions on the test set. The loss indicates how well the model's predicted values match the actual values, with lower values indicating better performance. The accuracy metric represents the percentage of correct predictions the model has made over the total number of predictions. After the evaluation, the results are printed out. The code snippet first prints the loss, followed by the accuracy in percentage format. The accuracy percentage is formatted to 2 decimal places for easier interpretation. Overall, this code is used to understand the generalization capability of the model, that is, how well it performs on unseen data, which is crucial for assessing its potential real-world application. The provided code is designed to visualize the decision boundaries of a model named model_8 for both the training set, x_train, y_train, and the test set, x_test, y_test. It creates a figure with a size of 12 by 6 inches and 2 subplots arranged horizontally, side by side. The first subplot displays the decision boundary for the training set. It sets the title of this plot to train and then calls a function named plot_decision_boundary with model_8 and the training set as arguments. The second subplot shows the decision boundary for the test set. It sets the title of this plot to test and again calls the plot_decision_boundary function with model_8 and the test set as arguments. Finally, it displays the plots with plt.show. The plot_decision_boundary function is not defined within this snippet, but it presumably takes the model and a dataset as input and plots the regions of input space that are classified into different categories by the model. This is a common way to understand how well the model has learned to separate different classes in the dataset. The purpose of this code snippet is to visualize the training process of a machine learning model by plotting the loss curves. The history variable typically contains the record of the training and validation loss, and potentially other metrics, for each epoch during model training. By converting history.history to a pandas data frame and calling .plot, it generates a plot with the data frame's plot function. The plt.title, model_8 training curves, command adds a title to the plot, labeling it as model_8 training curves. This title suggests that the plotted loss curves belong to the 8th model, which can be helpful to differentiate if there are multiple models or training runs being analyzed. The code will produce a line graph that visualizes how the loss metric changes over each epoch of the training process. This visualization is useful for understanding the learning process of the model and can help in diagnosing issues such as overfitting or underfitting by observing if the loss is decreasing and how it behaves over time. The code provided is a sequence of commands typically used in machine learning with TensorFlow to define, compile, and train a neural network for a binary classification task with a specific learning rate schedule. Firstly, the code sets a random seed using TensorFlow to ensure reproducibility of the results. The model named model_9 is defined as a sequential neural network with two hidden layers of 4 neurons each, using ReLU activation functions, followed by an output layer with a single neuron using a sigmoid activation function, which is common for binary classification tasks. Next, the model is compiled with binary cross-entropy as the loss function, the atom optimizer, and accuracy as the metric to monitor. A learning rate scheduler callback is defined that will adjust the learning rate at each epoch during training. The learning rate starts at 1 times 10 to the power of -4 and increases exponentially by a factor of 10 raised to the power of epoch/20. Finally, the model is trained, or fitted, on training data, x_train and y_train, for 100 epochs while passing the learning rate scheduler callback to use the defined schedule during training. This dynamic adjustment of the learning rate can help in finding an optimal learning rate for the model to converge more effectively during the training process. This piece of code generates a plot that visualizes the relationship between the learning rate and the loss metric during the training of a machine learning model. It is setting up an array of learning rates that increases logarithmically, created by multiplying 1 times 10 to the power of -4 by 10 to the power of numbers from 0 to 4.9 in increments of 0.05. As seen by the expression 10 np.arrange 100/20. The array of learning rates and the corresponding loss values, presumably from the training history of a model, are used to create a plot where the x-axis is on a logarithmic scale to more clearly display the wide range of values. The x-axis is labeled learning rate, the y-axis is labeled loss, and the title learning rate versus loss is set for the graph. This graph is often used to help choose an optimal learning rate for model training by showing where the loss decreases most rapidly with changes in the learning rate. The provided code snippet is a sequence of commands used to create, compile, and train a simple feed-forward neural network using TensorFlow's Keras API. Firstly, the random seed of TensorFlow is set to 42 to ensure that the results are reproducible. This makes the initialization of weights and other random operations in the neural network consistent across different runs. Next, a sequential model named model_10 is created with 3 densely connected layers. The first 2 layers each have 4 neurons and use the ReLU, rectified linear unit, activation function. The third layer has 1 neuron and uses the sigmoid activation function, which is common for binary classification tasks. The model is then compiled with the binary cross-entropy loss function, which is appropriate for binary classification problems. It uses the atom optimization algorithm with a learning rate of 0.02 to update weights during training. The accuracy metric is also specified to monitor the performance of the model during training. Finally, the model is trained on training data, x_train and y_train, for 20 epochs. An epoch is one complete pass through the entire training dataset. During this training process, the model's weights and biases will be updated in order to minimize the loss function, ultimately learning to make predictions on the binary classification task. This code is designed to visualize the decision boundaries of a classification model for both the training and test datasets. It does this by creating a figure with a specific size and then splitting this figure into 2 subplots, which are positioned side by side, as indicated by the 1, 2, 1, and 1, 2 arguments in the subplot function. The first subplot, titled train, will show the decision boundaries of model_10 as applied to the x_train and y_train data, which represent the features and labels of the training set respectively. This visualization is created by calling the plot_decision_boundary function with the given model and training dataset. The second subplot is similarly structured, but instead titled test. This subplot will show the decision boundaries based on the x_test and y_test data, which are the features and labels of the test set. Finally, the plt.show command is called to display the resulting figure with the 2 subplots. This visual comparison can provide insights into how well the model generalizes from the training data to unseen data represented by the test set. It is used to assess the model's performance and overfitting visually by comparing the decision boundaries on training and test sets. The purpose of this code is to evaluate the performance of a machine learning model, identified as model_10, on a test dataset. The dataset is composed of input data x_test and the corresponding target values y_test. The evaluate function computes two metrics, the loss and the accuracy of the model on this test set. The loss gives a measure of how well the model's predictions match the actual targets, typically a lower loss indicating better performance. The accuracy is the proportion of predictions that the model got correct, which is a common performance metric for classification problems. After the evaluation, the code prints out the calculated loss and converts the accuracy into a percentage format for easier interpretation. The accuracy value is formatted to show 2 decimal places. These print statements provide the user with a clear understanding of how well the model performs on unseen data, which is critical to determining its suitability for deployment or for further optimization and validation. This code snippet is purposed to create and display a normalized confusion matrix as a visual plot using the matplotlib library in Python. The confusion matrix is a table used to describe the performance of a classification algorithm by showing the correct and incorrect predictions compared to the true labels. Firstly, it imports necessary libraries and defines a figure size. It computes a confusion matrix CM from some predicted values y_preds and true values y_test. The confusion matrix is then normalized by dividing each row by the sum of its values to show relative frequencies of predictions for each true label. The number of classes, or distinct labels, in the matrix is determined by the shape of the centimeter. Next, it sets up a figure and an axis for plotting with the defined figure size. After that, it uses how to display the confusion matrix as an image in a specified color app. A color bar is added to the side of the plot to indicate the scale. The code decides whether to use custom class labels or numerical labels based on a Boolean flag classes. It then configures axis properties of the confusion matrix plot by setting title, labels for both axes, adjusting tick positions, and changing font sizes. It also determines a threshold value used to decide text color for visual contrast purposes on the matrix cells. Lastly, it loops over each cell of the confusion matrix and places a text label inside it that includes both the absolute count and the normalized percentage. Using either white or black text color depending upon a visual distinction threshold based on cell values. Overall, this code visualizes a normalized confusion matrix to allow better interpretation of how well a classifier predicted across different classes. The snippet of code is written in Python, and it is used to import the TensorFlow library, which is a popular machine learning framework, and specifically loads the FashionNIST dataset from TensorFlow's Keras API. The FashionNIST dataset is a collection of 60,028 by 28 grayscale images of 10 fashion categories, along with a test set of 10,000 images. The dataset is a drop-in replacement for the classic NIST dataset of handwritten digits. The code then proceeds to load the dataset and split it into training data, train_data, train_labels, and test data, test_data, test_labels. The training data consists of images and their corresponding labels that the model will learn from, while the test data is used to evaluate the model's performance on unseen data. The purpose of this code segment is to display the first sample of the training data along with its corresponding label from a dataset. The training data and labels are presumably stored in 2 separate variables, train_data and train_labels. The first line print, fTrainingSample, \n train_data 0 \n prints the first training sample, which is accessed by the index 0 from train_data. The formatted string fTrainingSample, \n train_data 0 \n includes the text training sample, followed by the contents of the first training sample, including a new line before and after it for readability. The second line print, fTrainingLabel, train_labels 0 prints the label associated with the first training sample. This is obtained by indexing into train_labels with the index 0. It prints the text training label, followed by the actual label of the first training example. Overall, this code is typically used to verify the contents of the dataset by inspecting the first example and ensuring that the data is loaded correctly and formatted as expected. It can be useful for debugging or getting a sense of what the training examples and labels look like. The purpose of this code is to display an image. It utilizes the matplotlib.pyplot module, commonly imported as PLT, which is a collection of functions that make matplotlib work like MATLAB, allowing users to create data visualizations easily. Specifically, the imshow function is called to show the 8th element, since Python indexing starts at 0, train_data 7, refers to the 8th item, in the dataset train_data. The semicolon at the end of the plt.mshow line is often used in Jupyter notebooks and other interactive environments to suppress the output of the last line, which can include text or object representations that are not necessary when the objective is solely to display an image. In this case, it is meant to display the image without any additional text or object output. When the code is run, it will open a window with a graphical representation of the 8th data entry in train_data, which is assumed to be an image data structure that Matplotlib can interpret and draw. There are no further customizations, such as title or axis labels, so only the raw image will be displayed. The purpose of this code snippet is to display an image from a training dataset and its corresponding label as a title on the plot. Specifically, the code uses the imshow function from the matplotlib.pyplot module aliased as plt to render the 18th image, index 17, as indexing starts at 0 in Python from an array named train_data. The color map equals plt.centimeter binary argument indicates that the image should be displayed in black and white. Following the image display, plt.title is used to set the title of the plot to the appropriate label for the displayed image. This label is retrieved by taking the 18th element from an array named train_labels and using this to index another array named class_names, presumably a list of string labels corresponding to distinct classes of the images in the training set. This code is typically used for visualizing the data in a machine learning problem to ensure that the images and labels are correctly aligned and make sense to a human observer. This code snippet is designed to visualize 4 random images from the fashionist dataset, which is often used for benchmarking machine learning algorithms in the context of image classification. It uses the Matplotlib library to create a figure and subplots for displaying the images. When executed, the code will create a 7 by 7 inch figure with a grid of subplots arranged in a 2 by 2 format, where each subplot will contain a randomly chosen image from the train_data. The index for the random image is obtained by selecting a random number within the range of the dataset's length. plt.mshow is used to display the image in each subplot with a grayscale color map indicated by map equals plt.centimeter binary. The title of each subplot is set to the corresponding label from train_labels, which is presumably a list or array that contains the labels for the training data. These labels are then converted to a human-readable format via the class_names list or array. Additionally, plt.axis false is used to hide the axes for a cleaner look of the images. This code, therefore, serves the purpose of providing a quick visual check to understand and ensure that the data is loaded correctly and to see examples of what the images in the dataset look like. This code snippet is a series of commands in Python using TensorFlow, a machine learning library, for defining, compiling, and training a deep learning model for a classification task. Firstly, the random seed is set to ensure reproducibility of results by initializing the random number generator in a fixed state. Then, a sequential model named model_11 is created using the Keras API within TensorFlow. This model has a simple architecture comprising an input layer that flattens a 28 by 28 dimensional input into a 784 feature vector, followed by 2 hidden layers with 4 neurons each using the ReLU, rectified linear unit, activation function, and an output layer with 10 neurons corresponding to 10 classes using the softmax activation function. Next, the model is compiled with the Atom Optimizer, a common choice of optimization algorithm that adjusts model weights based on the data. It uses sparse categorical cross-entropy as the loss function, which is suitable for multi-class classification tasks when the classes are represented as integers, and it sets accuracy as the metric for performance evaluation. Lastly, the model is fitted, on the train_data and train_labels over 10 epochs, and its performance is validated against test_data and test_labels. During training, the model updates its internal parameters, and after each epoch, the model's accuracy and loss are evaluated using the validation data. The code snippet references a method call to model_11.summary. The purpose of this method is to print out a summary of model_11, which appears to be a machine learning model, most likely a neural network given the context indicated by the comment. The summary typically includes information about the model's layers, their respective output shapes, and the number of parameters, both trainable and non-trainable, within each layer. The comment above the code explains that the model's shape includes a none value, which typically represents a variable batch size in the context of neural networks. The batch size is the number of samples that the network processes before updating its parameters, and leaving it as none allows for flexibility in specifying the batch size at runtime. The number 784 in the shape, none, 784, probably denotes the size of the input feature vector for each sample, suggesting that the input data to the model is flattened into a one-dimensional array of 784 features. This input size is common for images, for instance, 28 by 28 pixel images from datasets like NIST. The code provided initializes and trains a basic neural network model using TensorFlow and Keras. The use of tf.random.set_seed 42 ensures that the results are reproducible by setting the random seed for TensorFlow's operations. The model, named model_12, is a sequential model, which is a linear stack of layers. It consists of an input flattened layer that reshapes the input from a 28 by 28 grid into a flat vector of 784 elements. Following the input layer, there are two hidden dense layers with 4 units each in ReLU, rectified linear unit, activations, which add nonlinearity to the model. Finally, there is a dense output layer with 10 units corresponding to 10 classes, with the softmax activation function, which is common for multi-class classification problems. The compile method is used to configure the model for training. It specifies that the sparse categorical cross-entropy loss function should be used, which is appropriate for sparse labels and multi-class classification. It also sets the optimizer to Atom, a popular optimization algorithm, and indicates that accuracy should be tracked as a performance metric. The fit method trains the model on the training data, train_data with labels train_labels, for a fixed number of epochs, 10 in this case. It also uses separate test data and labels, test_data and test_labels, for validation. The performance of the model on both training and validation data across epochs is recorded in the norm_history variable. This training process adjusts the parameters, weights, and biases of the model to minimize the loss and improve the accuracy on the provided data. This code snippet is written in Python and uses the pandas library to plot data loss curves for machine learning model training. The pandas library is imported with the alias PD. Then, two data frames are created from dictionaries, non_norm_history.history and norm_history.history, that presumably contain the training history of two models. One trained on non-normalized data and the other on normalized data. With PD data frame non_norm_history.history.plot title equals non-normalized data, the code is plotting the loss curves over epochs or some other metric over training time. For the model that was trained on non-normalized data. Likewise, with PD data frame norm_history.history.plot title equals normalized data, it's doing the same for the model trained with normalized data. These plots are likely to contain lines representing the training and validation loss over time that allow for visual comparison of how the two different pre-processing approaches impacted the training of the models. By calling .plot on the data frames that contain the history, the code generates a line plot for each training history. The titles for the graphs are set to non-normalized data and normalized data correspondingly to distinguish between the two training scenarios. This visualization is helpful for comparing training convergence and can be used to determine whether data normalization had a positive effect on the model's learning process. This particular code is used for creating, compiling, and training a neural network using TensorFlow and Keras. The code starts by setting a random seed to ensure reproducibility of results. It then defines a sequential model named model_13 with an input layer that flattens the input data from a 28 by 28 matrix into a vector of 784 elements. The model has two hidden layers, each with 4 neurons and using ReLU activation functions, and an output layer with 10 neurons using the softmax activation function, which is typical for multi-class classification problems where the output is a probability distribution across different classes. The model is compiled with a loss function suitable for classification, sparse categorical cross-entropy, an optimizer, Atom, and it will monitor the accuracy metric during training. After compilation, a learning rate scheduler callback is created, which will adjust the learning rate during training based on the epoch number. Specifically, it multiplies the base learning rate, 1 times 10 to the power of -3, by 10 raised to the power of the fraction of the epoch number over 20. Finally, the model is trained using the fit method with the provided train_data and train_labels, including validation data to monitor performance on unseen data, and the learning rate scheduler is used as a callback. The model trains for 40 epochs, although there is a comment suggesting that fewer epochs might be sufficient given the current learning rate's performance. This code snippet is intended to plot the learning rate decay curve that demonstrates the relationship between the learning rate and loss metric during the training of a machine learning model, specifically how the loss changes with varying learning rates. It first imports the necessary libraries NumPy for numerical operations and Matplotlib for plotting the graph. It then creates a list of learning rates, LRS, which decays exponentially because of the log scale from 1 times 10 to the power of -3 or 0.001, increasing by a factor of the 10 raised to the power of NP.ARrange 40/20, approximately doubling every 2 steps within a range of 40 values. Next, the code uses plt.semilogs to plot these learning rates on the x-axis on a logarithmic scale against the corresponding loss values stored in find_lr_history.history loss, which seems to be a dictionary containing the loss metrics from a training process, not shown in the provided code, but it's implied. By using a logarithmic scale for the x-axis, the plot allows for easier interpretation of the loss behavior across many orders of magnitude of learning rates. Finally, it labels the x-axis as learning rate, the y-axis as loss, and sets the title of the plot to finding the ideal learning rate. The resultant plot is useful for selecting a learning rate that minimizes the loss, which could indicate an optimal learning rate for training a model. This code constructs and trains a neural network model using TensorFlow and Keras. It begins by setting a random seed for reproducibility of results. The model named model_14 is a sequential model, meaning the layers are stacked linearly. It starts with a flattened layer to reshape the 28 by 28 input images into flat 784 element vectors. Following this are 2 dense, fully connected layers with 4 neurons each in ReLU, rectified linear unit, activation functions. They serve as hidden layers in the network. The final layer is another dense layer with 10 neurons and a softmax activation function, which is common for multi-class classification problems. The model is then compiled with the loss function set as sparse categorical cross-entropy, which is suited for integer-labeled classification tasks. The Atom optimizer is used with a learning rate of 0.001 to adjust the weights during training. The model's performance is evaluated based on its accuracy. Finally, the model is trained, fit, on train_data and train_labels for 20 epochs, where it will learn from the training data. The validation_data parameter is set with separate test_data and test_labels, which the model uses to evaluate its performance at the end of each epoch, providing insight into how well it generalizes to new, unseen data. The purpose of this code is to define a function called make_confusion_matrix, which takes the true labels, y_true, and predicted labels, y_pred, from a classification task, along with optional parameters such as classes, fig size, and text_size, and creates a visualization of a confusion matrix. The confusion matrix is used to evaluate the performance of a classification algorithm. It shows the number of true positives, true negatives, false positives, and false negatives for each class. This function first creates a confusion matrix using sklern.metrics.confusion_matrix. It then normalizes this matrix by dividing each row by the sum of its values, which gives the percentage of true predictions for each class. The number of classes is determined by the shape of the confusion matrix. Next, the function plots the matrix using a Matplotlib figure and axis, with a color app that indicates the accuracy of predictions. Bluer colors represent more correct classifications. It adds a color bar for reference. Depending on whether the user has provided a class's parameter, it sets the axis labels with either the provided class names or ordinal numbers. The code also alters the x-axis to ensure that labels appear at the bottom of the plot. It calculates a threshold to set the text color in each cell of the matrix, using white text for dark-colored cells and black for lighter ones, to ensure readability. This text includes both the raw count and the normalized percentage for each cell. Overall, by calling this function with the appropriate arguments, one could visualize the performance of a classifier across different classes, making it easier to see which classes are being confused with one another. This snippet of code is used for making predictions on a dataset named test_data using a pre-trained model referred to as model_14. The predict method of model_14 generates a set of output values, likely probabilities, which are stored in the variable y_props. These probabilities represent the model's confidence in each possible outcome for the given inputs. Finally, the code slices the y_probs array to display the first 5 predictions using y_probs 5. This operation is commonly used to quickly inspect the model's output and verify its behavior on a few examples before proceeding with a more detailed analysis or further processing of the predictions. This code snippet appears to call a function named make_confusion_matrix designed to create and display a confusion matrix, which is a visual tool used to measure the performance of a classification algorithm. The confusion matrix is to be generated based on 2 sets of label data, y_true, which represents the true labels from the test set, in this case, test_labels, and y_pred, which represents the predicted labels made by the classification model, y_preds. The class's parameter is passed class_names, which likely contains the list of class labels that the classification task can output. The figsize parameter, set to 15, adjusts the size of the resulting confusion matrix figure, in this case making it 15 by 15 units in size, presumably inches or a comparable unit depending on the visualization library being used. The text_size parameter with the value 10 controls the size of the text within the matrix, likely adjusting the font size of the numbers or class labels displayed in the matrix to make them more readable. Overall, the purpose of this code is to create a detailed and well-formatted visualization of the confusion matrix to allow for better interpretation of the classification model's performance, where you can see how many instances of each true class were correctly or incorrectly predicted as each possible predicted class. The provided code defines a function named plot_random_image, which is intended to visualize a single image from a dataset, its predicted label, and its true label. It uses a trained machine learning model to make a prediction on a randomly selected image, and then plot that image. Within the function, a random index is selected, and the corresponding image is retrieved from the provided images array. The machine learning model, which is assumed to be already trained and passed as an argument to the function, is then used to make predictions on the reshaped image. The true label is also obtained using the random index from the true_labels array. The function then continues to display the selected image using matplotlib's imshow function, with the color map set to binary for a grayscale representation. It then sets the title of the plot with the predicted label, the prediction probability, and the true label. The title is colored green if the prediction is correct, i.e., the predicted label matches the true label, or red if the prediction is incorrect. Please note that this code snippet assumes the presence of other necessary imports and context, such as the matplotlib library for plotting PLT and TensorFlow TF for calculating the maximum probability for the predicted label. Without this context, the code as provided would not run successfully. This code snippet seems to be designed to display a random image from a dataset along with the prediction made by a trained machine learning model for that image. The function plot_random_image is being called with several arguments: model, images, true_labels, and classes. The model argument, model_14, is likely a pre-trained model, which is used to make predictions. The images argument stands for the data set test_data, from which a random image will be selected. The true_labels argument includes the correct labels, test_labels, for the images, which are used to verify the model's prediction against the ground truth. Finally, the classes argument represents a list or array of class names, class_names, corresponding to the possible categories the images can be classified into. What the code does is select a random image from the test_data provided, pass it through the model_14 to obtain a prediction, and then likely visualize both the image and the corresponding prediction plot side by side, comparing the model's prediction against the actual label from test_labels. It's a way of evaluating the model's performance on a single instance from the test set in a visual and potentially more understandable way. The purpose of this code seems to be to retrieve and list the layers of a pre-existing neural network model designated as model_14. By accessing the layers attribute of model_14, the code will enumerate all the constituent layers that were added during the construction of this model. This is typically useful for getting a better understanding of the model's architecture, including the sequence and configurations of layers such as dense layers, convolution layers, pooling layers, etc. This information can be used for debugging, model summaries, or modifying the model further. However, the actual execution of the line of code would be done outside of this comment, as this line serves as a placeholder or annotation indicating what operation is to follow in the actual code base. The code snippet you've provided suggests an operation where a specific layer from a neural network model, designated as model_14, is being accessed or extracted. The index 1 indicates that the second layer of the model, since indexing typically starts at 0, is the one being targeted. This kind of operation is often used in machine learning when one might want to analyze, modify, or reuse a particular layer of a pre-existing model. For example, it could be used for feature extraction, where the outputs of that layer are used as input to another model or process. However, without the actual code that performs an action on this extracted layer, we can only infer that the layer is being accessed or referenced by model_14.layers1. This code snippet is designed to extract the weights and biases from the second layer, index 1, as indexing starts from 0, of a neural network model named model_14. The specific method get_weights is called on this layer to retrieve both weights and biases associated with it. Following the extraction, it stores them in the variables weights and biases respectively. The comment in the code indicates that the shape of the weights matrix corresponds to the size of the input data, which is 28 times 28 for each neuron in the layer, and that there are 4 neurons in the layer. This implies that the layer is expected to have weights arranged in a manner such that there are 4 sets of 28 by 28 weight matrices, one set for each neuron. However, note that the comment might not accurately reflect the actual shape, as it appears to only be a human-written note and not an actual line of code that enforces or checks the shape. The last part of the snippet, weights.shape, indicates that the shape of weights is being evaluated, but without a print statement or any other action, this line doesn't affect the program and seems to be incomplete or an oversight by the coder. This specific code snippet imports the plot_model function from TensorFlow.keras.utils. The purpose of the function is to create a visual representation of a neural network model defined in Keras. The plot_model function takes the model as an input argument, here referenced as model_14, and generates a plot that illustrates the architecture of the model. By setting show_shapes equals true, the plot will also include information about the input and output shapes of the layers within the model, which can be particularly useful for understanding the data flow and dimensionality changes through the network. The resulting visualization can help in debugging the model architecture and in sharing the model design with others for collaborative purposes or for presentations. The code, as written, assumes that model_14 has been previously defined and represents a Keras model.